Greetings for the day. In this presentation, we are going to learn about the number systems. So let's learn what is a binary number system. Okay, it is the easiest way to give instruction through electrical signals. That is a two-state system, the on and off state. You know very well the electrical signals always are represented only through two states. One is on and off, or sometimes we call it as true or false, or a high and low state. So here for on state it is represented as 1 and the off state is generally represented as 0. The 0 means a no signal or a signal at a low voltage. A number system with 0 and 1 is called as a binary number system, and each binary digit is known as a bit. The binary number system has a base of 2. Why? Because there are only two digits here, that is the 0 and 1. 0, as said, it represents the low state and 1 represents the high state. The binary number is written within a parenthesis, and outside the parenthesis the base is represented. Okay, so only the base will tell whether the given number is binary or decimal or whatever it is. So if I put 2 outside the bracket as subscript, then it means it's a binary number system. If it is 10, it is decimal. If it is 16, it's hexadecimal, etc. Now let's see about the octal number system. Octal, we know that it is 8. Okay, so in octal number system, we have 8 digits into consideration, that is 0, 1, 2, 3, 4, 5, 6 and 7. That is, there are totally 8 digits which are considered as the base for an octal number system. Hence the base is 8 here. The sequence of the octal number system goes as 0, 1, 2, 3, 4, 5, 6, 7, then 10, 11, 12, 13, 14, 15, 16, 17, as such. Okay, each successive number, as we can see here, is a combination of two or more unique symbols of octal system after 7. Okay, so you can see here 0, 1, 2, 3, 4, 5, 6, 7 is given, and then we are getting the two digits 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Then again we get it as 2, 0, 2, 1, 2, 2, like that. So after 7, the octal system is a combination of two or more unique symbols. Next comes the hexadecimal number system. The hexadecimal system uses the numbers 0 through 9 and the letters A, B, C, D, E and F. And there are totally 16 digit and symbols. Okay, so it has 16 digit symbols and hence the base of hexadecimal number system is 16. So thus we have now gone through what is a binary number system. It has got only two digits 0 and 1 and the base is 2. And then the octal number system, which has got the base digits as 0 to 7, that is 8 number system, and the base is 8. And then the hexadecimal number system, which has got a combination of numbers 0 to 9 and then the alphabets A, B, C, D, E and F. Okay, and the base of hexadecimal number system is 16. And our normal decimal number system has got a base 10 because we use the numbers 0 to 9. Okay, so these are the very basics about the number system. Okay, this screen shows you the number equivalence, that is the decimal binary equivalent of the decimal, octal, hexadecimal, etc. Now let's see about the number conversions. So we're going to say about the decimal to binary conversion. The method of converting a decimal to binary is repeated division method. The rule is that whatever decimal number is given, keep dividing with the base 2. Write down the remainder and divide the quotient repeat till you get the quotient as 0. So now let's say an example of converting a decimal 25 to a binary number. So keep dividing 25 by 2. Okay, so 25 divided by 2 gives you 12 with the first remainder 1. 12 divided by 2 gives us a 6. There is no remainder, so the second remainder is 0. 6 divided by 2 gives us 3. Again, there is no remainder, so the third remainder is 0. 3 divided by 2 gives us a 1 with the fourth remainder as 1. So now from the last you have to move towards upward till the first remainder. From the fifth remainder to the first remainder we have to keep moving. So the binary conversion of 25 is 11001. So now we are going to see the binary to decimal conversion. To convert a binary number, follow these steps. The binary number system, the weight of each digit increases by a factor of 2 as shown in the example. The rightmost binary digit we call it as the least significant bit and the leftmost we call it as the most significant bit. We go for a calculation from right to left. Okay. So the first digit has a weight of 1, that is 2 power 0. The second digit has a weight of 2 power 1. The third has a weight of 2 power 2. The fourth has a weight of 2 power 3 and it keeps on increasing. So now what we have to do is multiply each binary number with 2 having the power 0 for the rightmost bit and then keep increasing to the left. So now after you multiply each, just add the products to get the desired decimal number. For example, here we are going to convert the binary 11001 to its equivalent decimal. So the rightmost bit we call it as the least significant bit and the leftmost we call it as the most significant bit. So the rightmost digit is 1 and it is multiplied with 2 power 0. The second right is 0 and it is multiplied with 2 power 1. The third digit 0 is multiplied with 2 power 2. Fourth digit 1 is multiplied with 2 power 3 and the most significant bit is multiplied with 2 power 4. So now let's find out the products of each digit multiplied with the bases. So for the first one we get it as 1 into 1 because 2 power 0 is 1. So 1 into 1 is 1. Second 0 into 2 is 0. 0 into 2 power 2 is again 0. 1 into 2 power 3 we get it as 8. 1 into 2 power 4 we get it as 16. So now let's add up. 1 plus 8 plus 16 gives us 25. So 25 is the required decimal equivalent for the given binary number. So we have to put it as 25 with base 10 to just represent it as a decimal number. So next is decimal to octal conversion. The method of converting decimal to octal is repeated division method again. For conversion, the rules are that divide the given decimal number by base 8. Octal means it has a base 8, so divide it with 8. Write down the remainder and divide the quotient by 8. Keep repeating till the quotient is 0. So now for example, if I want to convert the decimal 214 to octal. So now what we have to do? Divide 214 by 8. So 214 divided by 8 gives me 26 with a remainder 6. 26 when divided by 8 gives me 3 with a remainder 2 and then we cannot divide 3 further with 8, so the last remainder is 3. So now go from down to up, write down the reminders in that order, that is the third remainder to the first remainder. So the answer is 326 with a base 8. The next conversion is octal to decimal technique. So here now what we are going to do is, for converting an octal number to a decimal number, keep multiplying each bit by 8 power n, where n is the weight of the bit. So n starts from 0. Okay, how we converted the binary to decimal, something like that, very similar to that, octal to decimal. You have to keep multiplying each bit with its corresponding weight n. Okay, so now if suppose the given octal number is 724, okay, the base of 724 is 8 because I'm giving the octal number system. Now let's try to convert it into a decimal number. So here the least significant bit is 4 and the most significant bit is 7. Okay, so 4 is multiplied by 8 power 0, so it is 4 into 1, which is equal to 4. Then the second digit 2 is multiplied with 8 power 1, so 2 eights are 16. Then the most significant bit 7 is multiplied with 8 power 2, so we get it as 448. Now let's add up all the products. We get it as 4, 6, 8, base 10. Okay. So the octal conversion of 724 to a decimal gives me a 468 as the answer. Last technique is octal to binary conversion. In this presentation, so here we are going to learn how to convert each octal digit or 3-bit equivalent binary number. So consider an example of converting the octal 56 to its binary equivalent. This is just a tricky method to convert octal to binary technique, a little easier to understand. Consider the conversion of 56 to its binary equivalent. Now take the two digits 5 and 6. So take 4 to 1, 4 to 1. 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4. So now we know that adding 4 and 1 gives us 5. So we take those as the true value, that is 1 and 1, and we are not going to use 2, so make it as 0. Now adding 4 and 2 gives us 6. So take those two states as true state and 1 as 0. So now the binary equivalent of 56 is 101110 base 2. We'll be seeing the remaining conversions in part 2. Thank you.